Hey everyone, welcome to this video. In the previous video, we first learned about RNNs, and we will implement a very basic RNN to better understand what's happening in this diagram. Let's get started. So, in the course directory, please download this rnn.ipynb file and then upload it. You'll want to connect. For this code, we don't need a GPU. The CPU will be just fine. So we'll change the runtime type and confirm it's a CPU. And then just to save myself some time, I'll just do run all. And as this is running, or it should be done now, let me explain what all the code does. So we'll do some imports. And then let's declare some variables in this cell here. We'll have two features, such as breathing rate and blood pressure, so like health data, a hidden size of 3, which is the hidden state size. And remember that the hidden state is like the memory of the RNN, a batch size of 1, so maybe we'll just have one person, and time steps equals 24. As an example, 24 hours capture health data like heart rate, blood pressure every hour. And we will create our RNN right here. Everything should be pretty self-explanatory except for batch first equals true. And this will set the input shape to be batch size, time steps, and features. Ordered data can be stored as a rank 3 tensor. So, for example, every hour measure features equals 2, such as breathing rate and blood pressure. A day, or 24 hours of measurements, can be a rank 2 tensor of shape 24-2. And 30 people's measurements can be a rank 3 tensor, shape 30, 24, and 2. For our example ordered data, we'll pass in batch size, time steps, and features, and this will just be like random numbers. And let's print our example ordered data. So as you can see here, this can be thought of as every hour, measure two features such as breathing rate and blood pressure every hour for 24 hours, and this will be one single person. In fact, if we do a print example ordered data.shape, we get a shape of 1, 24, and 2. Now that we have our example ordered data, let's toss it into our RNN, and it will give two outputs back: the final hidden state and a history of the past hidden states. If we print the history of the hidden states, we get a lot of numbers here, which we'll come back to. And the final hidden state is like negative 0.34 and all these numbers. And as you can see, if we look at the history hidden states, the last one matches the final hidden state. So no surprises there. Now, for learning purposes, let's calculate the hidden state after the first time step manually for learning purposes. There will be input weights and hidden state weights. As I mentioned in the previous video, in this slide, yes, input weights and hidden state weights. So to grab these, we'll go through rnn.named parameters. So this is the input weights, the hidden state weights, the input biases, and the hidden state biases. And we'll just give these more descriptive variable names, which I do right here. And remember from the previous video in that slide as well, I stated that the current hidden state is equal to an activation function applied to hidden state weights times past hidden state plus input weights times the current input. I pasted that formula right up here so you can reference it whenever you want. And so, yes, let's calculate that current hidden state manually or by scratch to better understand what's going on in an RNN. So we'll set the initial hidden state to be zeros, and we'll print it. You can see here, the initial hidden state is all zeros. Now for this hidden state weights times past hidden state part, I'll say hidden to hidden is equal to torch.matrix multiply or matrix multiplication, hidden state custom, which is the past hidden state, with the hidden state weights plus the hidden state biases. For input weights times current input, we grab the current input. We'll say input to hidden is equal to torch.matrix multiply or matrix multiplication, the current input plus the input weights plus the input biases. And lastly, let's finish things off. Current hidden state is equal to an activation function applied to all of this stuff. So we'll say hidden state custom, which is basically our hidden state calculated manually or by hand. So hidden state custom equals torch.tanh. This will be our activation function. Now we have not gone over this activation function previously in this course because I don't find it to be very common. But yeah, just know that tanh is an activation function, and we need to use the tanh activation function to get the same results as earlier in our code. Cool. So the tanh activation function to hidden plus input to hidden. And here is our hidden state that was calculated manually. We get negative 0.1030. And this is the hidden state that was not calculated manually, as you can see in the history hidden states. And we get the same result. So yes, the point of this video was just to prove that everything mentioned in this slide is correct. And since we calculate the hidden state manually, you now know that, you now understand better what's going on behind the scenes in an RNN. Thanks for watching, and that's it for this video.